Las Vegas, Nevada. This entertainment oasis in the desert glitters and glows every day of the year. Here, lights move in luminous patterns, attracting people in continuous waves. To the east, 4,200 kilometers is Coney Island, New York, where the first amusement park illuminated by electric light still shines brightly today. Electricity is more than a force that humans have learned to harness. It is a natural phenomenon, found in the air and in our own bodies. What is electricity? And where in the world does it come from? It begins with the most basic unit of matter, the atom, which has a nucleus of protons containing a positive charge. Orbiting this nucleus are electrons, each containing a negative charge. The movement of negatively charged electrons between two or more atoms creates an electric current. Wearing protective clothing, a worker uses a conductor to check the electrical current. To produce a consistent current, electrons need to flow through a conductor. That's a material or substance with atoms that hold their electrons loosely, making it easier for them to move to another atom. Copper is used in most electrical wiring because it is an excellent conductor, as are most metals. Materials with atoms that hold electrons tightly, resisting the flow of current, are called insulators. Among these are rubber, plastic, and glass. These materials often are used to cover conductors to prevent people from being shocked. If you use a power source to move electrons along a conductor wire, you've got an electric current. Electric current travels along a pathway called a circuit. In some cases, as in these power lines in the West that carry electricity for hundreds of kilometers, it's a big circuit. Electric current is measured in amperes, or amps for short. When 6.28 quintillion electrons pass a point in a circuit in 1 second, that equals 1 amp. The force that pushes electrons along a circuit is called voltage. As voltage increases, so does the flow of energy. How do you measure the power of an electric current? By multiplying amps, or the flow of the current, times voltage, the force pushing the current along. The quality of the conductor also contributes to the strength of the current. But even when current flows through a good conductor, it will encounter some resistance. Resistance results in some energy loss and slows the flow of electrons. Resistance is measured in ohms. Remember, an electric current must travel along a circuit. There are two basic types of electric circuits. A series circuit provides only one path for current to flow along. In this example, if one light bulb burns out or the switch is turned off, the entire circuit is broken. No current will flow, and components on the circuit will not work. A parallel circuit provides the current with two or more paths. If a light or appliance burns out, the circuit is not broken. Current continues to flow to other components. Most households feature parallel circuits. Electricity is everywhere around us. Rub a balloon against the hair on your head and you'll create a charge separation, often called static charge. Rubbing increases the amount of contact and the amount of electron transfer. Eventually, this produces a spark known as static electricity. The most powerful form of static electricity is lightning. Lightning occurs in large cumulonimbus clouds because of charge separation. Many cloud scientists believe that charge separation occurs during the formation of ice pellets in the cold areas of the cloud. As supercooled liquid droplets begin to freeze, positive charges concentrate in the warmer regions of the freezing droplet. As the droplets freeze from the outside in, they develop a positively charged ice shell and a negatively charged interior. As the inside begins to freeze, it expands and shatters the outside shell, creating an electrical imbalance. The imbalance creates an intense electrical field, and electricity, a lightning bolt, results. The lightning neutralizes the opposing charges. The negative lower part of the cloud can also create an electric field with the positively charged surface of Earth. An electric field is created from each charged electric particle and extends outward from each particle. When that happens, lightning strikes the ground with a sudden flash of current 6 times hotter than the sun. Although humans still haven't found a way to harness the energy in lightning, we have found ways of turning other types of energy into electricity. Hoover Dam on the Arizona-Nevada border is one spectacular example. By blocking the flow of the Colorado River, the wall of this curved dam creates a place where water can fall with tremendous force. As the water falls, it strikes the blades of one of 17 turbines in the plant that rotate the shafts in the 17 generators. A series of magnets are connected to each shaft. As the magnets spin, they cause electrons to move in the wires and generate electric current. Constructed in the 1930s, the Hoover Dam today supplies 4 billion kilowatts of electricity a year to over 1 million people in California, Nevada, and Arizona. Just as electricity transformed a desert in Arizona and Nevada into a booming metropolitan area, so can it modernize this remote Brazilian village. A joint U.S.-Brazilian effort has brought electricity by means of solar panels. The panels contain materials that, by transforming sunlight, release electrons and ultimately generate electricity. The resulting electric current will run the water pump, delivering clean drinking water from deep underground. Lights and refrigeration will be available, as will communication with the world hundreds of kilometers away. This village, once fixed in the past, will now enjoy vital benefits that electricity provides.